So let's start afternoon lecture. The speaker is Professor Yoshinori Namikawa from Varieties.
Thank you very much for invitation. So I would like to, thank you very much for invitation. I would like to talk about the characterization of toric Hyperkahler varieties. So let me start with real symplectic manifold, real compact symplectic manifold of dimension 2n. Yes, and assume the n-dimensional compact torus acts on this symplectic manifold in the Hamilton way. So this is assume that this is a Hamiltonian action. Then you get the moment map, say M to the dual space of Lie algebra of this space. So this is the T is the Lie algebra. And this is nothing but Rn. Then the image of this moment map is bounded polytope, which is called the Delzant polytope. And so the situation is as follows. So this is a dimension n. N is two cases. The image is like this. This is image. This is a polytope. And the fiber of this map is, in the general point, the fiber is just n-dimensional torus. But here, on the edge, this is a one-dimensional torus, and on the vertex, the fiber is just one point. And in these situations, we can construct some toric variety together with Kahler form. And the Delzant theorem says that this M is nothing but this toric variety. So here is the moment map. And here, and delta. There is C infinity symplectic isomorphism compatible with the moment map. Yes. This is a toric variety. So toric variety is characterized as follows. So today I will talk on the holomorphic symplectic analog of these theorems. So so let me start with definition. X omega is a symplectic variety if the following holds of dimension 2n. If the following holds, this first X is a normal variety of C variety of dimension to n of C. And second, the regular part admits symplectic, holomorphic symplectic form, say omega, such that if you take some resolution, then omega extends to holomorphic 2 form on x tilde. Here, x tilde is a resolution. So if you have such a property for one resolution, therefore every resolution has this property. And this is a Bobile definition of symplectic variety. And a remark that this omega is a holomorphic 2 form, but may degenerate along exceptional locus. So if mu x tilde and extended together with extended, this is the extended 2 form, is symplectic, then mu is called symplectic resolution. Symplectic resolution. Yes. So now let's start with such a variety. Then the symplectic form on the regular part determines the Poisson structure on this manifold. But such a Poisson bracket extends uniquely to a Poisson structure on X. So from X, you get the Poisson bracket. And X is a Poisson variety. And for a function on X, let me define the vector field, Hamiltonian vector field, just by this. This is the derivation, and the derivation is considered as a vector field on X. Yes. This is Hamiltonian vector field. Hamiltonian vector field. Yeah. And this correspondence gives a map from the space of function to the space of vector field. X is singular, so theta x is just a dual of the Kähler differential. Yes. And assume that, now assume some algebraic group, say G, acts on this symplectic variety. So G preserves this symplectic form. And this action determines a map from the B algebra of G to the vector field. This action induces a map. And this action is called Hamiltonian. If this map factorizes as follows. So this factorizes in this way. If this map factorizes as in this way. Here, this is a map H, just defined. And here, this is the map. So this is called mu star. Mu star is G equivariant. Here, G acts on a joint way on J, and of course, G acts on this space of functions. And moreover, it preserves the bracket. Here, you have a B bracket. And here, you have a Poisson bracket. So this mu star preserves both brackets. So if this map factorizes as follows, then it is called Hamiltonian. If Hamiltonian action is given, then this map mu star determines a map from X to the gay star, the dual space, and which is called the moment map, a moment map. Moment map is not unique, but it's unique up to some translations or something. And yeah, so in this talk, not necessary, but you may assume X's are fine. But if you have this map, then you have a map of algebraic varieties. But anyway, you can assume X's are fine because I only treat the affine case. So in this talk, we assume the Hamiltonian action is G is n-dimensional algebraic torus. So in this case, the moment map is nothing but the following, and this is Cn. And this n is the possible highest dimension of such Hamiltonian action of algebraic torus. Because if you have a torus action, any torus orbit is contained in fiber because T acts on this space trivially. So every torus orbit is contained in the fiber. And you can check that by the property of moment map, it is isotropic. So n is the highest possible value, possible dimension. So this is a very special case. So
probably also assume that the action is favored. Probably also assume that the action is favored.
X is what?
Action is favored.
X action is what? Okay. So effective. So effectively action. Yes, faithful. Yes. So we assume that it's effective. Yeah. So the typical example is Toric Hyperkahler variety. Which is studied by many persons. For example, Goto, Bilowski, Dancer, Hausel, Stanfels, and Konno, and Proudfoot, and others. Many people have studied this object. So start with exact sequence of algebraic torus in some like this. Sorry, this is n, and this is n minus n, and this is. Start with n and large n and small n is some integer, positive integer. So let us consider some exact sequence of complex, algebraic torus. So if you take a character groups Then you have a map here like this. Tn algebraic group form Tn minus n C star is this. And this is Zn, and this is Z large N, and this is Zn minus. And this map is determined by some matrix, A and B. Yes? But if you start with such an exact sequence of free, rank-free modules, finite rank-free modules, then you can recover this exact sequence of algebraic torus. So now let's start with such an exact sequence determined by A and B, right? So we prepared 2n-dimensional affine space together with a standard symplectic form. The coordinate is given by Zn and W1, Wn. And standard symplectic form is given by the following way. Zi, I is 1 and n. Yeah, and Tn acts this space in the following way. Z1 to Zn, W1, Wn to T1, Z1, Tn, Zn, T1 inverse, Z1, Tn inverse, sorry, W1 and Wn. Yeah. Then this, of course, this action preserves this symplectic form, because this. And here, you have an inclusion of this map here. So n minus n dimensional algebraic torus acts on this space. And this is also Hamiltonian. So the moment map, the moment map, let's say mu of this action, C2n omega, is given by the following way. That here we have Cn to n and Z1 to Zn to W1, Wn. Then this map goes to, this is nothing but the dual space of this action, this torus, and this is given by sigma r. Now write A to be in this way. A is here, yes. So this is n times n minus n matrices, and take its column vectors, and then it is given by the following. Yes. And now, here you have a symplectic form, but you can produce new symplectic variety by using a symplectic reduction. So by using symplectic reduction, you can take the null fiber mod out by T n minus n. We call it YA0. Yes. This is a affine variety. This is nothing but, by definition, this is spectrum of the coordinate ring of the G-invariant part. Yeah. And so, by the holomorphic symplectic reduction, the original symplectic form induces a symplectic form here on the regular part. And so YA0 omega YA0 is symplectic variety in our sense. And the dimension is what? Dimension is just this is 2n minus n minus n usually, and this is is it possible? Yeah, and this is n plus n. So and divided by this, variety by this, so this dimension 2n. Yeah? Right. And but here, still this Tn action remains. So Tn acts on this variety. Tn acts on this variety. So we have and this is a Hamiltonian action of n-dimensional algebraic torus. Yes.
How do you check the extension property of this form?
Yes, because you can, if you can take a partial resolution. This is just you take some character. Yes, and if this character is 0, then the GIT quotient for 0 is just in this variety. But if you take alpha very general, then the variety becomes a symplectic variety with quotient singularities. So on the quotient singularities, the extension property is already proved in the Beauville's article.
So we need to suppose that this inverse should be norm or something like that.
Not necessary. Not necessary. If you can assume that it's it is irreducible, but you don't need this assumption. If you start with such a B, and if B contains some 0 rows, then exclude such things. Then the resulting variety is the same. And if the B has no 0 rows, the null fiber is irreducible, and everything is okay. Yes. Anyway, don't worry about that. Yeah. And so, as I said, this is if alpha is generic. This is a partial Clipant resolutions, and this is symplectic variety with quotient. But if A is unimodular, A is, or equivalently, B is unimodular. Unimodular means that consider this matrix A, and the unimodular means modular means any n minus n times n minus n minor has determinant 1 or minus 1 or 0. This is the definition of unimodular. If A is unimodular, B is unimodular. And if B is unimodular, then A is unimodular. It is called the Gale duality. And then this is symplectic resolution. Is symplectic resolution. Is symplectic resolution. Usually it is not smooth for even alpha is generic. So this is a typical example. And
Just a notational question. Where you put alpha, why what's the why for the symplectic resolution, for the partial resolution? Where you put alpha?
this one?
Is YA alpha?
Yes. YA alpha is just a mu inverse 0 mod out this with linearization alpha.
Zero means that.
Zero is a, zero is a character. This is alpha. So if alpha is 0, this. So let us give one more definition. It is called conical. An affine symplectic variety x omega is conical if this has a good C-star action. That means x can be written as a spectrum of some ring, coordinate ring, and this coordinate ring is positively graded. And the zero part is just a constant part. And second, this omega is homogeneous with respect to this C-star action. Homogeneous with respect to C-star action. This C-star action is called conical, so it has a unique fixed point. So this is a unique fixed point, which corresponds to the maximal ideal defined by the positive degree part. Yes. So you have some conical structure. So this is the, yes. Yeah, then our YA0, omega YA0 is a conical symplectic variety. Because here you have a natural scaling action. The scaling action is just this. Yes. And this scaling action induces action on this space. Because mu inverse 0 has a C-star action, and it descends to a C-star action. And the weight of this omega is just 2 in our case. Weight is just, if x is symplectic, then the weight is this And L is, this means that T star omega is to the power, T to the power L omega, some Z. And this L is called the weight of omega. And in our case, this has a weight 2. This is a weight 2, this, by this action. Yes. So this has also weight 2. So this is an example of conical symplectic variety of dimension 2n together with effective Tn action. So now let us state our main theorem. Theorem is the following theorem. So let x omega be conical, symplectic variety of dimension 2n with an effective Tn action, Tn Hamiltonian action, compatible with the conical action, conical cyst action. Yes. The T action preserves the symplectic form, but this conical cyst action doesn't preserve, and it has some positive weight and positive weight. So they are different action, and assume that. It's a commutative. T times C acts on this space. So assume X has a projective symplectic resolution. Okay. Then this variety can be written as follows. Here you have a moment map, and moment map, you choose this moment map so that the origin goes to the origin of the dual space of the Lie algebra. And here you have a YA, and there is some A, some N, and some such exact sequence, and some A unimodular, YA0 together with YA0. And this also has dimension 2n and this dimension 2n. And you have a map. Yes. And of course, this origin goes to 0. Then compare this map. Then there is a Tn equivariant. Phi is Tn equivariant as complex analytic, symplectic, complex analytic isomorphism. So it preserved omega and omega y. And which commutes with this action, with this moment map. And moreover, phi sends the origin of x to origin of y. Yes. This is the main result.
Does it compute with the conical action? Does it compute with the conical action?
No, not necessarily in my proof. But we hope that if you take some good C star, if you change the conical C star action, then this can be taken commutative with the C star, both C star, conical C star actions. Then it can be made, phi it becomes algebraic isomorphism. But at this moment, I cannot say that this is not algebraic. And yes, this is the theorem. So in the remaining, I will explain the outline of the proof. Outline of the proof. Yeah. So, how to use the conical condition? If you have a conical system action, then you get the, of course, this is the moment map. But if you have a conical system action, and usually this moment map factorizes to a quotient map of Tn, but this is isomorphic. And this is surjective. So X is conical. Then you get the following picture. So the moment map is nothing but a quotient map of the Tn action. So, and what is the behavior? What is the, let's look at the fiber of this mu. So a general fiber of mu is just Tn because of the effectivity. And there exists some hyperplane, say H1, HR inside the dual space, such that over which mu had singular fibers. So the situation is as follows. So you have this is the Tn star picture. You have a hyperplane. This hyperplane passes through the origin of this space. And H1, H2, HR. Yes. And and each HI is determined, described, written as the following. HI is the BI, eta is 0. Here, what is BI? BI is the element of one parameter subgroup of Tn. And this is identified with Zn, and it is naturally embedded in the Lie algebra of the torus. And this is a primitive, some primitive element. So it's a zero locus of some primitive element, Bi. Yeah. Moreover, what is the structure of the fiber? The fiber is as follows. You take some general point. So if you take eta general means that this eta is not contained in other HJs. It is contained in only one HI. This is the meaning of the general. Then we have a complete description. We have a complete description of mu around this point around eta. Yes. What is the description? Description is as follows. The local model is given as follows. So the local model is as follows. Here is the local model. The local model is in the following way. This is xy minus z mi is 0 times delta n minus 1. This is the torus, n minus 1 dimensional torus, and this is the disk of dimension n minus 1. This is a singularities. Yes, and this is a 2n dimensional space. And here you have a coordinate, theta 1, theta n minus 1, x, y, z, t1, tn minus 1. Yes. And the moment map is given in the following way. Delta 1 times delta n minus 1. This is delta n, which is given by the following way. This is z t1 tn minus 1. And what is the tn action? Here you have a coordinate, say lambda 1, lambda n minus 1, t. And this acts on this space in the following way. Lambda 1, theta 1, lambda n minus 1, and t x, t inverse y, and z, and t1, tn minus 1. Yes. So this is the Hamiltonian. And omega is just residue, symplectic form here. So z xy minus the mi plus the, which one is the first? T1. dt1, d theta 1. Yes. So symplectic form is given, has a following form. And it is a Hamiltonian action, and the moment map is given by the following way. This is the local description. Yes, so for hi, for each hi, we have a integer mi. So we define the discriminant divisor, define the discriminant divisor, h of mu as h is just mi hi. So you give a weight for by using this mi. Yes. Okay. Now we have primitive vectors, and now consider the following matrix. Say B, define B to be B1 to B1. So here B1 appears M1 times, and BR appears MR times. Yes. And the size of this matrix is just, we call, this is n, say, the size of n, and this is by definition, this is, so n times n matrix. Yes. So And if X has a symplectic resolution, we see that this B is unimodular. So we get the exact sequence of such things. B and A. Yes. A is also unimodular. So we compare X, omega, and toric Hyperkahler variety YA0, omega YA0. So how to compare it? Yeah. It contains some arguments. So X has a symplectic resolution. So you have a Poisson deformation. You have a smoothing by Poisson deformation. And the general fiber of such things is smooth, affine variety. And then for such varieties, Lozef studied the local structure of moment map, and the moment map, the discriminant locus is determined by the primitive vector. But such a hyperplane doesn't necessarily pass through the origin. So something like this. And anyway, you can prove that this is unimodular, right?
The torus extends to the smoothing?
Huh?
Does the action of the torus extend?
Yes. I will explain it later. So now we compare two moment map, YA0 and mu y. But let F be the locus where eta Tn star, eta is containing only one HI. So such a general point is excluded. Now in this picture, F is here. And exclude F from here. And restrict this X and YA0 over this base space. And we compare the both. Compare this. But here, the discriminant locus is the same, because if you take such YA0, then the BI is nothing but our BI. So the discriminant locus is the same. One can check that. And moreover, for such a point, if you exclude F, then on such a point, the local structure is the same. So this is only the gluing problem of the local structures. So we introduce sheaf. Introduce a sheaf, say odd x0 on this space Tn star minus as follows. So you take open set from here, then this is nothing but the Tn equivariant symplectic oath of mu inverse u. Yes. Then there's such a space. Space is classified. H1 oath x0 classifies. Such vibrations. The vibrations. And of course, x0 determines the zero element. But what is the element of YA0? But you can observe this odd x0 by using the following exact sequence. So you have an exact sequence O Tn star minus f to odd x0. And this is a map. If you take a section f, the function on the base space, and you consider the mu star f, and you consider the function on x, and it determines a vector field. And but if you start with the function of the base space, then this vector field is vertical to the fibers, and we can integrate it. So exponential to pi I, and it gives a automorphism of such things. And this gives a map, and it turned out to be, this is surjective, but there is a kernel. Kernel is just because by this form, this is a constant sheaf, and this is the dual of the character, co-character. This is the constant sheaf, and it is a linear function on this space. And this is both constant sheaves. And so what is H1 of this? So H1 x0 and H1 OTN star minus f, and so on. And here, 0 and 0. And this is isomorphic. But the codimension f inside this space is 2, as this picture shows. This has a codimension 2. So this is never 0. So this is never 0. So I don't know what is, I don't know if this is 0 or not. So we have a trouble. But so how to prove this? So how to prove the theorem? We need additional data. So here we use assumption that X has a symplectic resolution. So X has or YA0 has a symplectic resolution. Then this means that X or YA0 has a smoothing by Poisson deformation, flat Poisson deformation. A Poisson deformation is a deformation of the pair of the variety itself and the bracket. And it becomes a finite dimensional space, and so we take such a smoothing. Take such a smoothing. So here you have a smoothing of x over C1, and y, which is smoothing of y is 0 over C1. But here you have a sister action, you have a Tn action or sister action. But such action extends to the family. So Tn acts on this space. This is fiber-wise action. And conical sister action is, this is a conical action. So this action acts trivially on the space, but this sister action acts on the conical way, and this sister action acts on this space by scaling action by t to the power n. So, and you have the same things here and sister action. Yes? And if you have such a situation, you can get here is a relative symplectic form on the regular part and the relative symplectic form on the regular part. Yes? By using this, you have a relative moment map, so x, and relative say C1 Tn star times C1. And this is y. C1. The relative moment map. And this is also take sister equivariant and of course Tn equivariant. And now we have this is a family of moment map parameterized by the base space. So you have a discriminant locus over each fiber. So you have a relative. So you have a relative so you have a relative discriminant divisor. So here you have a discriminant divisor. Yeah. This is a relative discriminant divisor. And this is the same. Yes? And one can take say this f and f prime. So that this relative discriminant divisor is the same. What is the situation? The situation is this. Here, this is the base space of the moment map. Here. And this is C1. So this is Tn star C1. And here, this is 0. This is the original discriminant divisor this way. But on the general fiber is smooth. And the general fiber is like this. This is a parallel hyperplane. But they doesn't go through the same point like this. This is the situation of H. Yes? But here, such a point, the local situation is both local situation is the same. And here, this is over the general point, the general fiber is smooth affine, smooth Stein. So by using Lozev's result, the local structure of every point is the same here and here. So we compare, so and we exclude this space, exclude F from this space, and restrict it over such a space, and compare this relative moment map. The discriminant divisor is the same, and the local structure is the same, because F is here. But coordination F Tn star times C1 is in a case 3. So why it fails? Because this is codimension F is 2, so H1 is not 0. But here, the codimension F is 3. So this is the same. One can prove that this is the same. So there is a compatible isomorphism. And but this isomorphism extends to the isomorphism of this space by the Steinness or affineness of this X and Y, and restrict it to the center, to 0. Then we get the map from X to YA0 to Tn star. This is nothing but phi. So this is the outline of the proof. Thank you very much.
Any questions?
This smoothing that we consider, is it some version of the Hyperkahler deformation? This smoothing, is it some version of the Hyperkahler deformation?
No, this is my theory of Poisson deformations based on Kaledin's and Ginzburg's article. They call it twister deformation.
They call it
Twister. Maybe I think this has a Hyperkahler structure, and so this coincides with the twister deformation. But in general setting, this is some theory. We use the general theory of Poisson deformations. Yeah.
How do you decide the direction of the deformation?
So how I decide? It's rather complicated. If you take arbitrary one of such smoothing, but here the universal Poisson deformation of YA0 is completely understood. So you get some choice of the one direction. So you have a universal Poisson deformation, and you take a good direction. If you fix F and you take good direction on the universal Poisson deformation, then you get you can prove that this and this.
On the X side, you take arbitrary.
Eh?
On the X side, you take arbitrary.
Arbitrary.
About this modular.
Huh?
Without symplectic resolution, then you still can argue until you only need the modularity.
This one?
Yeah.
Uh-huh.
Then why you cannot go through is it?
Because without unimodularity, I don't know how it works, because we don't have, if X has non-symplectic resolution, we don't have such things. And smoothing is important because my theorem is based on Rose's classification of the moment map of Stein manifolds of Tn actions. So, yeah. So the problem is that problem or question, if X doesn't have a symplectic resolution, is theorem true or not? Yeah.
So if X doesn't have a conical cis direction, is it a function of YA0, or is it related to YA alpha?
No, because X is affine, X is Stein, but YA alpha is not Stein.
Right, but you can take a portion of YA0 as a discrete group.
And so we cannot simply compare X and YA alpha. Yeah. So for example, if X has only Q factorial terminal singularities, it is rigid. And so we cannot compare. Of course, the candidate exists, but this argument falls because of these conditions. So we need another different argument. Yeah.
So let's speak again.